Welcome to the lesson on additive manufacturing. Upon completion of this lesson, learners will be able to define additive manufacturing and its fundamental principles, discuss the key technologies of additive manufacturing with their respective advantages and limitations, and recognize the various applications and implementation of additive manufacturing technologies in the electric vehicle industry. Additive manufacturing, abbreviated as AM, is a revolutionary manufacturing process that creates objects by systematically depositing materials layer by layer, in contrast to traditional subtractive manufacturing methods such as milling, turning, grinding, etc. This technology has become particularly significant in electric vehicle production as well, offering several key advantages. AM enables rapid prototyping and testing of components, allowing manufacturers to quickly iterate and optimize designs. It is used in producing simple to complex lightweight parts and on-demand spare parts manufacturing, reducing inventory costs and improving supply chain flexibility for EV manufacturers. Let us discuss some of the additive manufacturing technologies that serve various manufacturing needs. These include fused deposition modeling, selective laser sintering, stereolithography, and selective laser melting. Each technology has found its specific niche in manufacturing, from prototypes and tooling to functional end-use parts and complex metal components. We will discuss each of these technologies in the following slides. Fused deposition modeling, abbreviated as FDM, stands out as one of the most accessible and versatile 3D printing technologies in today's manufacturing landscape. FDM works by pushing thermoplastic filament through a heated nozzle, methodically building up objects one layer at a time. FDM works with a variety of materials, from basic polylactic acid, abbreviated as PLA, to more engineering-grade materials like acrylonitrile butadiene styrene, abbreviated as ABS, polyethylene terephthalate glycol, abbreviated as PETG, and flexible thermoplastic polyurethane, abbreviated as TPU. What makes FDM particularly attractive is its cost-effectiveness and widespread availability, making it a go-to choice for both prototyping and hobbyist projects. While the final parts boast good mechanical properties suitable for functional use, you might notice visible layer lines in the finished product, though this rarely impacts performance. Selective laser sintering, abbreviated as SLS, is another additive manufacturing technology that creates solid parts by using a high-powered laser to fuse powdered materials into solid parts. The most common materials used are nylon or polyamide. One of the key advantages of this technology is that it eliminates the need for support structures during printing, as the unfused powder naturally supports the parts being built. This makes SLS particularly effective for producing complex geometric shapes and functional components that require good mechanical properties. The process delivers detailed resolution throughout the printed parts while maintaining consistent material properties from top to bottom. The next AM technology is stereolithography, abbreviated as SLA. This technology uses an ultraviolet laser to cure liquid photopolymer resin layer by layer, producing highly detailed parts. The process delivers better surface finish and accuracy compared to FDM, making it particularly suitable for visual prototypes. A visual prototype is a mock-up model that focuses primarily on the aesthetics and dimensional aspects of a product rather than functional features. SLA excels at producing small features and intricate details, achieving precision down to 25 microns. While the process requires support structures during printing, these can be removed with minimal marking on the final surface. The technology supports a wide range of specialized resins, including clear, tough, flexible, castable, and dental materials, providing versatility for different applications. The fourth technology is selective laser melting, abbreviated as SLM. This technology uses a high-powered laser to fully melt metal powder particles, building dense metal parts layer by layer. The process can produce complex components using various metals, including titanium, aluminum, and steel alloys. SLM requires careful process control and an inert atmosphere to prevent oxidation and maintain part quality. Support structures are necessary during printing to manage thermal stress and prevent warping. This technology has found significant applications in the aerospace, medical, and automotive industries, where it's used to produce functional metal components. Here's the comparison of the four key additive manufacturing technologies: FDM, SLS, SLA, and SLM. FDM uses thermoplastics with 0.1 to 0.3 millimeter resolution and offers low cost and ease of use, but shows visible layer lines. SLS works with polymer powders with a print resolution of around 0.1 millimeter, good for complex geometries without supports but requires careful powder handling. SLA utilizes photopolymer resins to achieve high detail and smooth finishes, but produces relatively brittle parts. SLM processes metal powders with a resolution of around 0.02 to 0.1 millimeter to create strong, complex metal parts, but involves high costs and complex post-processing requirements. Each technology's choice depends on specific application needs, balancing factors like material properties, resolution, cost, and finish quality. While additive manufacturing offers great potential in electric vehicle development, its current limitations prevent full-scale mass production implementation. This technology excels in specific areas that don't require high-volume output. During the rapid prototyping phase, manufacturers can quickly iterate designs and conduct functional testing of components, significantly accelerating the development process. For tooling and fixtures, the technology proves valuable in creating custom assembly jigs and 3D printed molds for composite parts, although these are typically produced in limited quantities. The production of specialized end-use parts, such as lightweight structural components and complex cooling systems, remains constrained to low-volume applications due to speed and cost limitations. In battery component manufacturing, while the technology enables the creation of optimized battery casings and intricate cooling channels, these applications are currently best suited for specialized or limited production runs. The spare parts sector also benefits from this approach, as on-demand production capabilities reduce inventory costs for low-volume replacement parts. In summary, additive manufacturing is a process that builds three-dimensional objects layer by layer from digital models. Various technologies support this manufacturing method, including FDM, SLS, SLA, and SLM, each offering distinct capabilities for different manufacturing requirements. In the EV production landscape, this technology finds its place in prototyping, tooling creation, battery component manufacturing, and spare parts production, though it faces limitations when it comes to mass production scenarios. Given these characteristics, the technology currently serves best in specialized and low-volume production within the EV industry, making it a valuable tool for specific applications rather than full-scale manufacturing. Thank you.